Hello, hello, my friends. Today we're writing a contest, participating, I'd say, and unfortunately, many of my friends will not participate because they said they are in airports. I don't know. It's like all of them in a single moment are in airports. They're waiting for a flight. They cannot participate, so the duel will not be very big. But we still have a lot of nice strong participants, so we will have several duels today, nevertheless. We're going to have 9 problems to solve in 3 hours, and maybe I will go for these harder problems, because that's what makes the contest more amazing when you look at all problems. So derangement is if BI is not CI for all i's. Um, You're given an array A of length n. We can delete an element from A, and we want to find out whether it's possible to perform some operation so that it is a derangement. How to do it? I think we want to keep only 2 elements. So if it's sorted, then it is a derangement. Yeah. So yeah, vi a int n. If not read n, then false. Vi a n read a. Find dance. I think it's bool. Yeah, it's bool. No, it's vi. So if ans empty, print no, else print yes. For from I from 0 to n. What? Print ans I, not n. Ans I and this. Okay. So now we want to find ans. Find ans will be vi. And let's check if it's sorted. So if a I minus 1 is greater than ai, then we return ai minus 1 and ai. Else, no, not else. Here we return nothing. That's it. That's basically it. So no. Yes. What's wrong? Ah. It's so slow now. What's wrong with you? Dude. No, yes, 5. I need to print the size as well. So no, yes. Mm-hmm. Good. Problem B. This problem differs from problem G. We need to find the minimum sum of prefix minimums after the most one operation. So we have an array of length n, satisfying 0 from ai from n, and we want to make the following operation at most once. Choose two indices I and j, set ai equals ai plus aj, and aj set to 0. So we take some element to the right of some element, make it 0, and add it to some other element to the left of it. And we want to find the minimum possible value of sum of all prefix minima. Prefix minima. We want to minimize it. I think we just want to make a2 0, I think, yeah? We just want to make a2 0. What does it do if I make it a2 0? When I make a2 0, I think I either want to make a2 0 or a3 0. Yeah, so what choice do I have? I can make, so I have a1, a2, an. I can make a2 0, so the answer will be a1 plus a2 plus 0. Or I can nullify a3, and then I have a1 plus minimum of a1, a2 plus a3, and plus and 0. So what's better, a2 or minimum of a1 and a2 plus a3? Also, I can add it to here, but it will be a1 plus a3 plus minimum of a1 plus a3 and a2. But probably it's just bigger because a1 vanishes. And here I want to say that minimum, I want to say that a2 plus a3 is bigger than this minimum, and a1 plus a3 is also bigger than this minimum, and this is true. So probably I just want to choose from these two options, right? So how can I prove that? If I change, so if I nullify a2, then I get this. If I don't nullify a2, I get at least a1 and plus minimum of a1 and a2 plus something. Ah. I think I always want to add the element to the previous one, right? So if I add, I always want to make this number smaller and this number bigger, right? Is it true? No. I always other way. I want this number to get bigger and this to get smaller, or not, or not. Or not. So it's such a stupid problem. Why do I spend so much time on it? So I always can make a1 plus a2. So okay, let's consider two cases. First case is a1 is smaller than a2. Then whatever I do, I will get A1. I will get at least minimum of A1 and A2. Right? I will always get A1 and I will always get A2 or A1. Okay, if A1 is at least A2, then definitely I will get A1 plus A2. The problem is that sometimes I would like 2 times A1. Okay, I think the answer is A1 plus A2. Is the answer just this or this? I don't understand. Yeah, so I think the answer is simply... Why am I spending so much time on it? I'm slow. I'm very slow. It's bad. So I definitely want... So if... Okay. And if... And return minimum of A0 and I think minimum of A0 plus minimum of A1 It's always the answer. This is the answer. Right? Yeah, I think it's just always the answer. 2, 2, 3. What am I printing? Yeah, that's always the answer. But I was slow. It's even not funny how slow I was. Okay, problem C. My god. 13 minutes. It's shame. Okay, problem C, we have an array A of n positive integers. AI divides AI plus 1. And he multiplies some elements in B by X. Any number x that Bob could choose. So we're given an array B, and we want to find value x such that after we divide some elements by x, we get that AI divides AI plus 1, right? Okay, let's try and do it. So let's go. We have, oh, I didn't have to do it. Okay, so we have some elements a1, a2, a3, etc. an, and in the end we get by b1, b2, etc. bn. So if it always each element divides the next one, we are fine. If at some moment it's not true, then some bi does not divide bi plus 1. But that means that we cannot divide both of them because that wouldn't change anything. And we cannot divide bi plus 1 by x. So we only divide bi by x. Oops. We only divide bi by x. And we divide it by some divisor of bi. So what do we know about x? X divides bi. It's the first thing that I know. The second thing is that x is divisible by bi divided by GCD of bi and bi plus 1. That's because x is also divisible by bi over x is divisible by divides bi plus 1. So it divides by, okay, that's fine. Yeah, so we know these two things. Then we go on and we again know something. I think we can just take GCD of all such BIs and that's it. Yeah, I think we just can take the GCD of all such BIs. Okay, let's go. So we have some vector of integers. So we start with 0 and we go like this. So if AI plus 1% AI, then X is GCD of X and AI, and return X. Okay, and let's compile that and let's take the test. So here, also if X is 0, let's take like maximum of X and 1, I think. So any number, then what? I can take just this number, yes, I see. No, I cannot take. I cannot. This is the problem. This is a problem, yeah, because I The problem is that I divided bi by this x, but now the previous number has some troubles, right? Okay, what if we take LCM of all such numbers? If we take LCM of all such numbers, we get the minimum possible x. We get the minimum possible x. Is it true that we can... So, what do I want to say? I want to say that if we have several numbers, and we take the minimum possible x among all such pairs, such bad pairs, where this number is not does not divide the next one. If we take the minimum one, then we are fine. Why is that? Because assume that there is some correct answer. So there are some segments like this. Okay, what happens? So inside the segments, everything is fine. Inside this segment, it was dividing this number, but now we replace x. So bi divides bi plus 1 over x prime. Now we replace x prime with x, which is smaller, so this is bigger. So this should work. Yeah. What about this border? So here we have bi over x prime, and it divides bi. Okay, but actually, yeah, I think we can just take the LCM of such numbers. So we'd start with 1 and we'd replace it bi over GCD of bi plus 1. Okay, so we just always say that so we take AI divided by GCD of AI and AI plus 1. Take LLG equals X, GCD of X and U. And we say that X should be, so X should be LCM of X and U. So instead of that, we say X times U divided by G. And now we just multiply it by U over G. And we return X. Okay, so now we have 1, 2, 2, 6. Can we have here true? Yes, we can. Okay, probably that's fine. Amazing. Probably works. Now problem. Okay, problem D, I guess. Make a palindrome. We select two integers L and R. So we take a segment of length at least k. Then we select an index I between these in this segment, where AI is the kth smallest number out of the subarray. Good. Then we delete AI from A, concatenating the remaining parts of the array. Determine if it's possible to get an array that is a palindrome to any number of operations. So if k equals 1, then we always can do it. So what I want to say? I want to say that let's consider k minus 1 least elements. K minus 1. So I claim that I can take k minus 1 least elements and make a palindrome out of them. Yeah, that's what I claim. I claim that we can make a palindrome out of several smallest elements. And that's the criterion. Okay, I think I can figure out the algorithm now. So what? We can only take a subsegment. I think we can take... Yeah. Kth, exactly kth element. Exactly kth element. I think it's fine. I think it's fine, yeah. So read the array. Bool ans. Ans, yes. No. So how to find this bool? Okay, first of all, I want to find the element which is exactly kth. K. Okay, k is the length, right? K is the length. I would say that k is the length. No, k minus 1 is the length. So this is the length that I want to get, right? Okay, how do I act? How do I act? So I first of all want to find kth order statistic. Okay, I found the kth order statistic. It's now here. Now I take bk. And now I want to construct a palindrome as big as possible with these elements. So let's do it. So vi smaller and equal. That's what I have. I have an array of smaller elements and the array of numbers of equal elements. That's what I have. So let's go int I from a. So if I is less than e, and equal starts with 1. So if I is less than e, then smaller push back I and equal push back 0. Else if I equals e plus plus equal dot back. Okay. Now I want to check two things. I want to check that smaller is a palindrome and that equal is big enough. So let's go. First of all, vi reverse smaller equals smaller. Then let's reverse it. So if smaller is not equal to reverse smaller, then return false. Otherwise, I want to find the number of elements that I can get. Ans equals smaller dot size, and for int I from 0 I is less than equal dot size over 2. Okay, like this. So I want to say that answer plus equals minimum of answer and or minimum of equal I and equal dot size minus 1 minus I. And also if equal size percent 2, then ans plus equal the minimum middle element of the array. So return ans is at least k. I think that's it. Let's compile. Yes, 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 no, no, yes, no, yes. Ah, the last one is wrong. So 1 to 2, 1 to 2. I am saying that you cannot get a palindrome. But of course you can. Why am I saying that? Reverse smaller is yes. Answer equal is of size 2. K is 3. Ah, 2 times this. Of course, 2 times the minimum. Yes, and now we can solve the all tests. Yes, 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 no, no, yes, no, yes. Right. Good. Okay, problem E. Not exactly fast. Make it 0. You're given an array A of n positive integers. We select array B of size n such that the following properties hold. B is at most A for any index, and every problem is about some weird awkward arrays. There exists an index I, not the last one, such that everything up to this index is equal to the sum after this index. Then we subtract bi from ai. What? Your task is to change all the elements to 0, find the minimum number of operations required. Then output a way to perform the operations. And we need at most 17 operations to do that. Okay, something like a binary logarithm. Consisting of n positive integers. So what would I like to do? I would like to do this. I would like to start with going from the left and the right side. Each time I take, so I just take it greedily. I take this sum as far as I can and this sum as far as I can, and I keep them almost equal. At some moment, what do I get? I get that this sum is equal to this sum and some part of this addend, possibly zero part, or vice versa. So I have left part, for example, which is taken fully, and the right part is not taken fully. It is taken it's taken, but always also some part of this addend is added. However, if I subtract it now like this, I will get into trouble because what? Wait, what? We cannot do that. Sometimes there is no solution. Yeah, sometimes there is no solution. Yeah, sometimes there is simply no solution. I think there is either one operation or two operations needed to do that. That's what I think. I think there is one or two operations. Why do I think so? First of all, if the sum is odd, then impossible. If the sum is odd, then it is impossible to do. Also, if there is an element which is bigger than everything to the right, or element is bigger than everything to the left, then it is also impossible. Why? Because each time, for example, element is bigger than everything to the right. No. No, it's not true. But I will now understand what's true. So actually, so what is my preliminary algorithm? So first of all, let's make this a greedy walk. At some moment, we get this full segment, and also we want to add some part of this element here. If this is just the place where we want to do it, and this sum is just equal to this sum, then it's true. If we can take all these elements but the remaining part is odd, then impossible. But also, for example, let's consider the following. So we have some sum s here. Here we have some s minus d, and here we have element e, and s minus e plus d is greater than s. So d is greater than plus e minus d. So, and it is the same parity. So d is less than e and same parity. Then I want two operations. Firstly, I want to subtract something from here and from here. And secondly, I want to proceed. So first of all, I want to subtract something from here and from here, and then I want to proceed. However, I think that sometimes if S... So how much I want to subtract? I want to I want this E to become equal to D. That's what I want. I want E equals D. No. What? I want this to be equal to S. So I want to subtract. So I want this sum to be exactly S. So I want to subtract E minus D over 2 from here and from here. The problem is that it can happen that S minus D is less than E minus D over 2. What does it mean? It means that 2S minus 2D is less than E minus D. That means that E is greater than 2S minus D. So E is greater than everything else. But I think in that case it is impossible. Okay, so let's solve this problem. I think I found this out. Okay, false VIAN. VL. So then VL ans equals find ans of A. And if A is empty, then return, not return, but what? Print -1. Else we print ans.size. Then we print a lot of arrays. It should be VVL. So for V from ans, good. That's it. So now we have VVL find ans const VL A. Let's go. So I want to go from right and from left side. So VVL ans. Are the elements positive always? Yeah, the elements are always positive. Okay. Okay, so okay, let's make it easier. The LLANS equals accumulate A dot whole A and 0LL. Okay? You don't know what accumulate is? Okay. This is so stupid. Okay, so if ans %2 is 1, return nothing. Return ans. Return nothing. Okay, SMH equals MS over 2. Now we want to find the first place where the sum is at most SMH. Index left equals 0. Okay, let's like this. So what do we want? We want to say that if left sum plus a left is greater than SMH, then we break. Otherwise, we left sum plus equals a left. The same way we go from right to left. So if right sum plus a right is greater than SMH, then break. Otherwise, right sum plus equals a right. And we subtract one from right. Good. So there are two cases. First of all, if right is less than left. In this case, it's extremely easy, and we simply return this whole array A. So we return simply A. Okay, the second case is that right equals left. What do I do then? Then I ask, is it true that oh no. No, I'm not right. I'm not right. Unfortunately, I'm not right. Okay. So if right is less than left, then we have 1. And we return A. What's the next case? The next case is that element A is bigger than everything else. So if A times 2 is greater than if A is greater than SMH, then also return impossible. No, not A, but A left is greater than SMH. Return nothing. Also, there are more cases. So first case is if right sum is equal to SMH. What then? Then I don't want it. I don't want to do it like this. Yes, I simply have an element. E. Here I have S1 and here I have S2. Then I want at most 2 operations. So first of all, what do I want? What do I actually want? No, I don't. No, everything is fine. Everything is fine. Actually, I want to copy it, I think. I think I want to subtract something from here. Now it becomes equal to this one, and then I subtract from there. So what do I want to do? So I have some right sum. It's left sum. Left sum. I subtract from E and from S2 something, so that left sum becomes equal to right sum plus E. That's what I do. I think I want it in the other order. I want to subtract from S1 and from E something so that it becomes equal to S2. So how do I do that? I do that the following way. So first of all, if right, so I want to find out some disbalance. I want to take something that I want to subtract from the left part. So now in the left part, there is left sum plus a left. This is what I have in the left part. In the right part, I have right sum. I want them to become equal, so I need to subtract this over 2 from both things. Why is this at least this? So why L plus M is at least R? Ah, it's obvious. It's probably obvious. Okay. I want to subtract this. So if subtract is greater than 0, then I want to add something to the answer. So answer dot push back VL of size A. What? Why don't you know what ans is? I have defined it here. Oh? What? It's happening. What's happening with you? Ah, I see. I'm an idiot. Okay. So if subble greater than 0, then ans push back VL of size CZA. Now what do we do? First of all, I want to say that answer left, ans 0 left is, it's better to say back. Ans back left is equal to subble. Then I go from 0 to CZA plus plus sign. So addend is minimum of subble minus accumulated and AI. Then ans.back I is add. Accumulated plus equals add. And AI minus equals add. Good. And now I want to say that if max element of A is not 0, then answer push back A and return ans. It was a struggle, but finally we have gotten out of it. 1, 1, 2, 3. What is that? One, 1, 2, 3 minus 1, 2. What is this? Ah, plus equals. I see. Why? So 1, 1, 0, 0. So it becomes 4, 2, 1, 5. And then 4, 2, 1, 4, 2, 1, 5. Ah, I understand. Because I am AI minus equals dot back I. Okay, now it's good. Now problem probably F1 and F2 is what we need. What do you think? 57 minutes on these problems. That took tourists 23 minutes. That's sad, to say the least. Okay, problem F1, I think. You are given an initially empty array A. You may perform the following operation any number of times. Choose a number S and append a cyclic shift of the array to the end. Append a cyclic shift of this array to the end. Okay. Okay. It's acceptable. You are also given an integer n and m, restrictions of the form AI is not equal to x. Count the number of distinct arrays of length exactly m that can be constructed using the Lawn operation and satisfy all the given restrictions to array considered different if they differ at least at any position from 1 to n. Print the answer modular FFT modulus. Okay, I think it's just dynamic programming. So for each I, we want to find out the number of arrays of length exactly I that follow, that satisfy all the restrictions. Then we iterate over all possible ways of proceeding. How many ways of proceeding? So what is the asymptotics? N times n times n. N times, yeah, n times n times n. Yes, I think n times n times n. Okay, probably we can do it in square time, in cubic time. Solve test, find dance. So we just read n. And the restrictions. False VPIIAN read x and y. I think let's just subtract 1 from x and from y. Then int find dance NA and print ans. So what do I do here? First of all, I want for all the restrictions to know where they are. What do I actually want? What do I actually want? Okay, I know what I want. I know. So vi ans of size n plus 1. Initially, we have one empty array. In the end, we will return ans.back. So let's go from 1 to n. And we want to fill ans I. In the process, we iterate on how many. I think we already know. Yeah, okay, let's go from int j from I think we need to start with this and then think on how much we add. So we start with 1 and I plus j is at most n plus j. Before that, we want to find all the restrictions. So VVI restrictions of size n. And we say that On the position X, we cannot have Y. Okay, good. Okay, good. So let's look at all the restrictions in so let's say that let's look at the restrictions. So I look in W, I plus J minus 1. So what do I see in W, I plus J minus 1? Actually, what I see at all at some moment, I have some array. So here I, for example, see number 7. What does it mean? It depends on whether it's 0, 1, 2, 3, 4, 5, 6, if it is 7th index or not. So if a restriction jth is 7, for example, yeah, we see. So if j is at least, at most 7, no, at least 7, this means that 0 is not at j minus 7th position. I think we can just make a Boolean array, VB forbidden of size 2n plus 1, I don't know. And we want to find out what was forbidden and what was not. And we say that this restriction says that 0 cannot be on the position j minus q j minus 1 minus q plus n. So on this position, we cannot have anything bad, right? We cannot have 0. Now we want to find out where the 0 can be. So we do this, then we want to do what? We say that it is true. So for int j from 0, not j. Okay, possibles. Okay, from 0 to j. So where the 0 can be. So if not fk and not k plus n and not fk plus n minus j, then plus possibles. Then we say that answer I plus j is sum of answer of I plus j and product of answer I times possibles modular m, where m is I need mod, and modular mod. That's it. Let's go. So I want to see 701 65045. Not quite. Why? Why is it 7? 111, 112, 121. Ah, 121 is 2 times. Oh my god. 121 is 2 times. Okay, so we need to make some fix. We might need to make some fix. So what to do with 121? I want to think that we always have to take 1, 2. However, is it the only way that something's wrong? For example, 1, 2, 3, 1, 2, 1. Are there exactly 2 ways to do that? 1, 2, 3, 1, 2, 1. 1, 2, 3, 1. Can we just say that simply taking 1 is forbidden? No, we cannot say. Maybe we can never start the segment with 1. If we start segment with 1, and then we have something, instead of that, okay, here we have 2 ways to do it, right? 1, 2, 3, 4, 1, 2, 3, or 1, 2, 3, 4, 1, 2, 3. Okay, I think we can just say that if we have a segment that starts with 1, then the next one cannot start with 1. It can. We forbid a segment that starts with 1, and then there's just a segment of only 1 1. Maybe like this? No. We need to forbid something, but I don't understand quite what. So we have a segment, we have a segment, we have a segment, we have a segment. So let's look at it. Let's look at it. So first of all, if we have some intermediate segments, it doesn't matter too much because each time one of them gets smaller, it just takes one element and gets bigger immediately. But it needs to take the same element as before. Therefore, it comes down to the last and the first segment. And it might happen that we make it one longer and this one shorter. But it can only happen if this is the maximum element of both of them. This can only happen if this is the maximum element of both of them. So do we simply forbid for example, in this case, we have 1, 2, 3, 4, then 5, 1, 2, 3, 4, then 1, 2, 3. Instead of that, we could take 1, 2, 3, 4, 5, 1, 2, 3, 4, we could do this, but also we could do 1, 2, 3, 4, 5, 1, 2, 3, and 4, 1, 2, 3. I don't understand really how to eliminate this possibility. I don't know. This is a crazy problem. This is a kangaroo problem. I don't have any idea what to do here. Okay, first postulate. I think that for any segment of segments, there are one or two ways to divide them. One or two ways. No, for example, here it's bigger because I have 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3. Mm. Okay, this can only happen, some problems can only happen when I have some segment starting with 1, ending with the maximum element, and then the next segment also starts with 1 but ends with m minus 1. This is the only problem, isn't it? Probably. How to... So let's simply say that for this segment, I remember if it started with, if it ended with something like this. Because in this case, the next segment cannot, the next segment cannot be from 1 to m minus 1, right? Let's just forbid that. Let's just say that I forbid. So let's say that if I have several ways of dividing, I need the leftmost segments to be as small as possible. Let's say that. The left segment should be as small as possible. Okay, let's try this somehow. I don't know. So this says, this counts the number of ways to make a segment, an array which ends with 1, 2, etc. I. So ans 0, 0 is 1. So the easy answer is this. But it is wrong because I did not subtract something. I want to say that if I have the last segment 1, 2, etc. m minus 1, then I don't count the previous one where it was 1, 2, etc. m in the end. Because that was forbidden. So let's say that if f n is possible, then ans I plus j 0 is difference of ans I plus j 0 and ans I j plus 1. However, now I also need to calculate these answers with ans I plus j and something. But I can't do it because I can say that ans I plus jj is what? Okay, let's write like this. If not fn, then ans this is equal to ans I0. Probably something like this. Now it doesn't make sense because now it's 44. Okay, what happened? Sorry. So sometimes I have too big answer. How? 55 and here 65. But how? Now I don't understand anything. Ah, there is also a problem like this. So 1, 2, 3, 1, 2, 3, 1, 2. Ah, and it's fine because this is forbidden. But I also could make it 1, 2, 3, 1, 2, 3, 1, 3, 1, 2. Yeah, probably I could. Why is it 65? Why is it so big? How is it 65? 2, 3, 4, 2? Okay, what if I have just 65? 60. 144? So on the element I plus j minus 1, we have number q. Then at element this, we have potential 0. No, let's do it like this. On this element I plus j minus 1 minus q plus n. So let's take the real position and add n to it. So the real position of 0 could be I plus k plus n. Why is it 55? What if q is very big? What if q is very, very big? Now it makes sense. I don't understand a single thing about this. Okay, for example, this one. 3, 2 to 3, 3, 3. So I have 3 elements, and here it is not 3, and here it is not 3. What is the answer? They say that the answer is 5 for some reason. Okay, what are the answers? The answers are 1, 1, 1, 1, 1, 2, 1, 2, 1, 2, 1, 1, and 3, 1, 2. 5 answers. It's correct. Let's look at it. Answer 4000. 4000. Yes, 4000. Why do I think that it is 5? Okay, 0, 1, 2, 3, 4. 0, 1, 2, 3. What I think about the answer, about the correct answer. So when the length is 0, the answer is 0. The answer is 1. Okay, when the length is 1, then I think that... No, I don't understand something. J plus 1. Okay, when the answer is 1, how many ways of doing it? 1, but it also ends with 1. So I need to write like this, 1, 1, 0, 0. And we see it. Okay, now 2. For 2, we can start either with 1, 2, or 2, 1, or 1, 1. This is what's possible. So the answer should be... So here I have two ways of continuing that. So 1 times 2 is 2, and plus this 1 is 3. But there is one way where it ends with 1, and one way where it ends with 1, 2. So 1, 1. So it should be 3, 1, 1, 0. However, I see 2, 1, 1, 0. Why do I have 2, 1, 1, 0? To find that out, I forbid... How did I forbid that? No, I don't understand. So I equals 2. Let's see when I equals 2. I equals 2. And I did not add something to the answer. Okay, let's start with I equals 0. And j equals 2 I want. I want j equals 2. Okay, j equals 2. I forbade something. Possibles is 1. Why is possibles 1? No, I don't understand. No. Okay, so f... Okay, so q equals 2. And we say that 0 plus 2 minus 1, 1 minus 1 and plus n is 2. F2 is false. So the fact that this cannot be 3 so I actually add 3 to everything. So the actual indices are 3, 4, 5, 6, 7, 2, 1, 0, minus 1. So we found out that I plus j minus 1, which is 1, cannot be 3. So this cannot be 3. No, this cannot be 3. So this cannot be 2, this cannot be 2. This cannot be 1, this cannot be 0. So I found out that this cannot be 0. This cannot be 0. But this only cannot be 0 if the length is at least 3. This only cannot be 0 if the length is at least 3. Okay, so if Q is less than J, then this, else delayed Q plus 1 push back this. And then we iterate over everything delayed in J and say that FQ is true. Now it's 5. 71 now. Seven three 7-3-1-0. 7-3. Ah, it should be n plus I. Seven zero one 65 045 random number. Okay, no, it does not work. The heck? Okay, I don't know. Okay, probably the best option that I have is to not just print the answer, but also how to get such an answer. I unfortunately need to get how I can get such the answer. Okay. Okay, let's do that. So now instead of this, I need to list all the answers. Okay. So I go through this and do this. And okay. Mm-hmm. Now I want to say that for int k from 0. Iterate over k and iterate over what? Iterate over answer. So what do? I say that so if I know that 0 is at some position, then I need to push back what is at pth position. If I know where is the 0th position, I need to push p minus k modulo j. And then I need to add it to answer I plus j 0. But I don't want also if k is 0, I also want to add it to I plus jj. However, if the previous segment so if k is 0 and find ans I j plus 1 begin ans I j plus 1 dot end is not equal to pause is not equal to end. I need to write what I want to find. And then continue. I don't feel well. Vector subscript out of range. Which one? 0, 4? Why? J is 3? Just for you, my friend. What is happening? And why is happening? $100? Ah, okay. Let's say 11. It's now always 7s? I only want to iterate over possibilities, over possibles. $74, but last time it wasn't 74. It was what? Come again? 71, I think. No, it was 74. Okay, instead of finding ans, let's sort it and print it. So sort ans back all begin. Ans back all dot end. For okay, here we have 74. Okay, 0, 1, 2, 3, 4, 0 is repeating. Okay, it happened, of course. Okay, I actually never want a longer and then a shorter segment starting with the same. So it's not only j plus 1, but it's j plus anything. Okay. $66, almost there. Still not quite. Okay, 0, 1, 2, 0, 1, 0. How is possible? It's possible. So there are two ways to do this still. There are still two ways to do it. So I could end with 0. I have 0, 1, 2, 0, 1, and 0. Or 0, 1, 2, 0, 1, 0. Oh my god. What? So I have two ways. Let's see. 0, 1, 2, 0, and 1, 0. Or 0, 1, 2, 0, 1, and then 0. So this passes 2 to this one. No, this passes 1 to this one, and this passes 1 to this one. So if I have something that started with 0, and then I append an array which also ends with the same element, then I actually need to add that to... What the heck? So probably I need to say that if answer so what is the last element of this thing? If the 0 is at the kth position, if the 0 is at the kth position, then at j minus first position, there is j minus 1 plus k. J minus 1 minus k. And that means that the previous array cannot be j minus k. So I say that answer I plus j minus k is sum of answer I plus j minus k and answer I j minus k modulo mod. I hope that's enough because it is crazy. Why? $60 fucking 4. Maybe I'm subtracting something twice. I need to abandon this solution and just write from the scratch because this is crazy. This is freaking crazy. Okay, let's do it the other way. Let's say that I just do it greedily. I just always do it greedily. What do I do greedily? I see some element, for example, u. I go up until it gets to some number something, w. Then I go to 1 and I continue until I see u minus 1 and I stop. Again, I see some element. I go up until I get some other element, then I have to get 1, and then I go until I see t minus 1. Stop. The only way that it can happen not this way is if I start with 1. Then I just go up until I can. So now I want to prove that if I do this, it is correct. So this is correct. This is always correct. The question is it correct that I go up until I can? If I cannot, what happened then? It means that I have actually 1 etc t, and then I have some segment t plus 1 etc q, and then 1 etc t. But instead of that, I have taken from 1 to q. But this is fine because this is just fine. So let's say that I always take it greedily. If I always take it greedily, then it is forbidden to start with 1 and with something, I don't know, t, and then start the next segment with t plus 1. This is the only thing that is forbidden, to start with 1, to end with t, and start the next segment with t plus 1. Anything else is fine. Okay, so let's calculate how many ways there are to end my segment with 1 etc t. Okay, basically the dynamics is same. However, in the process, I do everything here and I ignore this, I think. So ans I plus j 0 is sum of this, but I need to ignore all the answers where I start with some number t plus 1, but the previous segment was 1 etc t. Okay, so let's do it. I need to ignore all the segments. So I need to do three things. First of all, I need to calculate ans I plus jj. And I can do it if this is true. So this is basically 100% correct. I can do it always. Yes, I can always do it. Yes. However, I also need to find out how many answers are not correct. So to do that, I basically here need to iterate over all other case other than okay, I can do it here. I think I can just do it here. So let's say if k, then what? K is basically j. So j minus k. At the 0th position, I have j minus k. So like this t plus. I think I mean here I have t, here t minus 1, so here t. So this element is just the length of this segment. And I need to forbid ans I plus j0 is difference of ans I plus j0 and answer I j minus k modulo mod. That's it. Yeah, that's it. So this has to be 65, I hope. Now it's wrong for some reason. For some completely other reason. And we have another great opportunity to debug this. So 3 answer 4. What's wrong with you? 4? Ah, it should be 4. Six two one one. 3110. So let's again compose our table. So 1000. Then I want to see one segment, but it is 1. So 00. Then I want to see 3 answers like this. And then I want to see. So what answers do I have? I have now 1, 1, 1, 1, 2, 2, 1, and empty. So it gives us 1, 2, 3, 2, 3, 1, and 3, 1, 2. This gives us 1, and then I cannot have 2, 1. So I only can have 1, 1, 2. Here I can only have 1, 1, 1. Here I can only have 1, 2, 1, and this is okay. And finally here I have 1, 2, 2, 1, 1. So this is 7 answers. But this is saying me 6 instead of 7. And I want to find out why. Let's try and do it. So 1. Ah. Okay. Answer 3. Then it should become 4. And then it should become 6. It should become 7. I simply need to eliminate all of this, I think. Yeah? I think I need just to eliminate all of this. That's what caused the issue. You say what? Such a third of the solution. And such a third of me. Okay, now I have a great problem of solving this F2 version. And for F2 version, I also need to... What is the asymptotics? 5000. So probably not the cubic solution is what I need. Why do I have a cubic solution in the first place? Okay, so this 4 is fine, this 4 is fine, and even this 4 is fine because it's still 5000 times 5000. So this part is not cubic. And this part is not cubic. Four. Okay, this is bad. This is bad, but instead of let's call it find dance faster. Find dance slow, let's call it. So what do I do in find dance? So first of all, so it's again 4, 4. This is fine, but then I have this 4, and this is 5000 cubed, which I don't like. So instead of that, first of all, I can simply say so we can say like this. So this is good. And also I can say that answer I plus j 0 is sum of this and this. In this case we can eliminate possibilities at all, and it still should work. Yes, it still works. Now the only thing that I want to remove is this huge cycle, which is very slow. Also, probably I have here 25 million integers, which is 100 million bytes, which is 100 megabytes, but this is fine. So what? Maybe this can be done with bit sets? Is it fine to do it with bit sets? Oh my god, I don't want to do it with bit sets. I really don't want to do it with bit sets. Bit sets are messy. So what do we basically have? Basically, in the inner cycle we have some two types of messages. We have the messages of type that these are forbidden, and also we have messages that these are forbidden, and this thing moves to the right. This thing moves to the right. And what do I need to do? I need to take conjunction of these two things. It is a binary array. And I need to take a dot product with not a dot product. Yeah, a dot product with something else. It's convolution. Oh, freak. I don't want to calculate this with convolution because it will be a frustration. That's it. I don't have a choice though. I don't have a choice. So, what I want to say that I need to multiply basically two arrays. I need to prepare two arrays. Oh my god. Okay, first of all, this can be done. It is fine to do. Fine thing to do. So now I can simplify like this. So this is the cycle I want to speed up. This is the cycle I want to speed up. So what do? Repeatedly. So first of all, let's just write all the restrictions. They say two things: that I cannot have start here, 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 here. And they say that I cannot have start, there is this thing, and I cannot have start Here, 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 here. And each time they match, it adds something to the answer. Yeah, each time they match, I add something to the answer. But I subtract what the hell happened here? I don't know still. Why I need to delay some operations? Can I always do this? Or not? No, for some reason I still cannot. I don't know why. Hate it. So not only it still it just doesn't work. It just doesn't want to work. So we basically have several ones like this, several ones like this, and these three says that here we cannot have 3, here we cannot have 2, so here we cannot have 0. But we can have here 0. Okay, so I have several ones which say that this can be multiplied by this. I need to make two multiplications. One where I add something and one where I subtract something. So to add something, how to do that? I don't know. I don't understand why there are some delayed freaking operations. Why should they be in the first place? Maybe let's go from the other end. No, I will not solve this problem. The most probable outcome is I don't solve this problem. But let's go from the right end. So I want to find the ith answer. I want to find the ith answer. To find the ith answer, I want to iterate over where I could start. And also I have some forbidden numbers. So ans I is sum over j from let's say that I is the length. So this is I and this is I minus 1. So j could be anywhere from 1 to I. And I take this segment of length j. So I take answer, we are counting 0. Answer I minus j 0. Times the restriction array. The restriction array says whether it was possible to put it like this. How to calculate the restriction array? Let's assume that, first of all, for example, this number is at most 0, this number is at most 1, this number is at most 2, etc. If this was so easy, No, this is worse. This is even worse because if I have some 3, it starts doing different things for different... No, I need to go from left to right. I need to go from left to right to say that these 3 definitely... Okay, let's go from left to right. So I want to say that ans I plus j 0 plus equals so again, there are 2 types of restrictions. One that say that 0 cannot be at some position, and there are still problems with them actually. Yeah, for example, it says that this is not 3. We can deduce that this is not 0. However, of course it can be 0 if the array is simply shorter than this. Therefore, it's bad. It's just bad. Maybe that's why we need bit sets, but for bit sets I don't know any way to calculate fast dot products. I don't know fast way to calculate dot products because there are not any. If this element is bigger than what I wanted, then so what do I have? I have 3 types of queries. I have such queries. So make some true to false. First query is make some true to into false. Second query is do it the same thing here. Third query is make a dot product of this and inverted this, which is simply a multiplication of polynomials. Yeah, multiply these 2 polynomials and find some coefficient of this product. Yeah, so find some coefficient of the product of these 2 polynomials. Maybe if I can edit FFT fast, but I don't. I cannot do it because FFT is the value of some polynomial. If I change in some points, and if I change its coefficient, then all n values change a lot. No, I cannot keep track of the FFT of this polynomial. Okay, find some coefficient of the product of these 2 polynomials And also the next thing that I need to do, and is instead of zeros and ones here, I have ans I j minus k, something like this, and do the same thing. Find some coefficient of the product. So I have two polynomials, and sometimes they change. Sometimes they change. And then I need to multiply two polynomials. And unfortunately, the changes can happen all over the place. They can happen in the first coefficient, in the last coefficient, in the middle coefficient. And I need to find some coefficient of their polynomial product. So this is the change of the first of or the second. You know what I mean? Okay, I can replace two multiplications with one if I initially take the polynomial of ans I0 minus ans ij minus k. So if I take such polynomial, then it is just one multiplication, not one multiplication, but oh my god. Okay, I give up. This problem is something. This is sad. Okay, since this is so sad, I will make very fast editorials and finish on that, with that. Okay, problem A. Problem A says to us that we have an array, and we want to find out whether we can make a derangement of it. Derangement is an element which is not on its correct sorted position. All elements are such. So the problem asks us if there is a subarray of the array A, which is a derangement. So if we sort B and make B sorted, then this is not equal to this is not equal to this, etc. So to solve this problem, you firstly need to think, are there any simple derangements? So if you have only one element, you cannot make a derangement, because any element x in the sorted order it's just still x, and x equals x. So you cannot make a derangement. Now two elements, x and y. If they're same, then after sort they're still the same as x and y, and it is not a derangement. If x is less than y, then also you don't get a derangement. But if you have x is greater than y, then after sort they are y and x, and this is a derangement. So the simplest derangement is of two elements. Now you ask yourself, can we make a two-element derangement? And the answer is yes, if and only if B is not sorted. So if B is sorted, then there is no derangement actually, because any subarray is also sorted, and sorted subarray cannot be a derangement. And if it is not sorted, then there are two consecutive elements such that the first of them is bigger than the second one. And if there are such elements, then you can leave only them by removing all other elements. You get only these two elements. They are a derangement, and you win. So you simply check whether your array is not sorted. If it is not sorted, you print, for example, 5, 2 here, because 5 is greater than 2. Problem B, minimize sum. You have an array A of length n. You need to take two indices I and j such that I is less than j, and set aj to 0 and ai to ai plus aj. You want to find the minimum value of such sum. How do you find it? So, your answer is a1 plus minimum of a1. Let's say that B is the new array. B is the new array. Plus minimum of B1, B2, and B3. Plus, etc. Plus minimum of B1, etc. Bn. You want to find the minimum value of such sum. And they say that we do at most one operation. So let's, if we don't make any operations, then we get a1 plus minimum of a1, a2 plus minimum of a1, etc., an. Well, actually the answer to this problem is these two addends. So the answer is a1 plus minimum of a1 and a2. This is the answer. How to prove it? Well, obviously there are two cases. There is a case when a1 is at least a2, and there is a case when a1 is at most a2. They intersect, of course, when a1 equals a2, then both cases hold. But if I consider some of the cases twice, this does not make the solution false. And my reasoning incorrect. So the first case is a1 is at least a2. Then this answer written here is simply a1 plus a2. Yeah, because minimum of a1 and a2 is a2. How to get such an answer? Very easy. You take your array a1, etc., an, and you perform operation with a2 and a1. So you add a2 to a1 and set a2 to 0. So you get this array. And then the minima are as follows: a1 plus a2, 0, 0, 0, 0, etc. So they are all just zeros. So you get a1 plus a2. And note that you cannot get less than a1 plus a2. Why? Because if we make operation with a2, then the answer is indeed a1 plus a2. Now let's assume that we don't make an operation with a2. Then I claim that b1 plus minimum of b1 and b2 is at least a1 plus a2. I claim that. Why do I claim that? Because actually b1 is at least a1. You did not nullify a1, so it is at least a1. In a similar way, this is at least a1 and this is at least a2. You did not make them 0. Okay? So this is at least a1 plus minimum of a1 and a2, and minimum of a1 and a2 is a2. So this is at least a1 plus a2. Therefore, I have proven both lower bound and upper bound. You can get this answer, and you cannot get smaller. Okay, the second case, a1 is at most a2. a1 is at most a2. There are two subcases. One very trivial subcase is n equals 2. So your array is simply a1 and a2. Then you can do nothing and simply achieve a1 plus minimum of a1 and a2 which is a1 plus a1 a1 plus a1, which is 2a1. Okay, the second case is n is at least 3. Then you can perform the operation with a3 and add it to a2. So you get the array a1, a2 plus a3, and a lot of zeros. So this minimum will be a1, and this minimum will also be a1, just because a1 is less or equal than a2, and you even get to add a3 to a2. It still makes the a1 the minimum. And then you get a lot of zeros. This is 2a1. So again, you get your upper bound on the answer. It is 2a1. Let's prove that you cannot get lower than 2a1. Again, that is because you have b1 plus minimum of b1 and b2. And there are two cases. First case is that you didn't touch, you did not make this operation as written here. If you did not make this operation, then this is at least a1, this is at least a1, this is at least a2, and this sum is at least 2a1. The second case is if you did the operation that nullified b2, a2. But if you nullified a2, then all of its contents got into b1. So now you have at least a1 plus a2 plus a1 plus a2 and plus 0. a1 plus a2. But if your answer is at least a1 plus a2, this is actually at least 2a1. So still you get at least this answer. So by not very big case consideration, you just print this sum. Okay, problem C, subset multiplication. You had some array A in which each element divided the next one. And you are given an array B which is achieved from array A by multiplying some elements by same integer x. So he did this to some elements. You need to find any number x which could be if you have this array B and you're guaranteed that there is some array A that was before the operation. Okay, as I said during the contest, let's look at two elements bi and bi plus 1 such that bi does not divide bi plus 1. If there are no such pairs of elements, then you can actually take x equals any number, because we just can take empty subset S. We didn't, so A is just same array as B. We did not do anything. We simply automatically have an array A with condition that each element divides the next one. So let's consider the case when there is such pair, or maybe even several pairs, in which this happened. You can actually argue that bi is x ai and bi plus 1 is just ai plus 1. Why is that? Because if you only multiply ai plus 1 by x, but not ai, then ai obviously divides x ai plus 1. Also, ai obviously divides ai plus 1, and also xai divides xai plus 1. So these three cases are impossible. You could not multiply ai plus 1 by x, and you could not multiply ai by x. In both of these cases, you automatically get that bi divides bi plus 1. So the only way in which this indivisibility happened is that bi equals to xai and bi plus 1 equals ai plus 1. Good. Now what do we know about x? We know two things. First of all, so we know that xai does not divide ai plus 1. No. This is known, but we don't know x. Let's write it in term. We don't know AIs because we only know BIs because they're given. So let's write it in terms of BIs. So we know that BI is XAI and BI plus 1 is equal to AI plus 1. In other words, AI is BI over X and AI plus 1 is BI plus 1. And we actually know that AI divides AI plus 1. Let's write that. First things first, we know that x divides bi. Also, we know that bi over x divides ai plus 1. This means that bi, wait, no, bi plus 1. Bi divides x bi plus 1, and that means that x what can we say about that? What can we say about that? When you have such a condition where both numbers bi and bi plus 1 are known, you want to figure out what you know about x in this case. Usually when you do that, when you want to do that, you need to factor out GCD of two numbers. So actually, anytime when you have something that divides something, what you really want to do is you want to factor out some GCD of these two numbers. Okay, let's do that. Let's say that Gi is GCD of bi and bi plus 1. What is that alternative definition? Alternative definition is just is that Gi is such a number that Gi divides bi, so that Gi equals bi hi. No, bi. Bi equals Gi hi. Bi plus 1 equals Gi hi plus 1. And you know that hi is an integer. Hi plus 1 is also an integer, actually a positive integer. And you know that GCD of hi and hi plus 1 is equal to 1. Let's write this divisibility. So Gi hi divides Gi hi plus 1 times x. That is what we know. When you have a divisibility and these both numbers are non-zero integers, you can factor them out. So we can actually say that hi divides hi plus 1x. But now you see that these two numbers are coprime. When you have two coprime integers and one of them divides the product of another one and x, then you can simply remove hi plus 1. The simplest way to prove that is to look at the factorization. And in factorization of this number, there are no primes that are also in this number. Therefore, if this number is divisible by hi, all primes supplied into this product to be divisible by hi are supplied by x, not by hi plus 1, because hi plus 1 is coprime with hi. So actually we know that hi divides x. Okay, so we know that two things: x is divides bi and x is divisible by hi, which is equal to bi over gi. I claim that if such number x exists, then you can just take least common multiple of all such numbers. You can just take the least common multiple of all such numbers. Let's prove that. Let's take our array A1, A2, etc. AN. Let's look at the optimal answer. Not optimal, just any answer. Where instead of x we have y. Y is probably not equal to this least common multiple, but if it is equal to it, then we automatically proved that it can be such a number. Okay. Then what? Let's look at the set S. Set S looks like this. It is some segment of consecutive integers, then some numbers are not taken in S. Then again we have some set, then not taken, then taken, then not taken. Okay. First of all, let's make it so that this bound only happens in places where this bi does not divide this bi plus 1. So I claim that you can assume that the end of the segment only happens in places where bi does not divide bi plus 1. For that, let's look at the smallest set S, the smallest size of S. And I claim that if what I said before is false, then you can make a smaller S. Okay, let's assume that you have found such a place. Here we have some segment, it ends somewhere, and here we have AI, which is bi over y, and here we have AI plus 1. And here we have bi plus 1 and bi plus 1. So AI divides AI plus 1. Let's assume that bi also divides bi plus 1. Then actually I could take this set S one element smaller. What happened then? So I remove this from the segment. So I want to check that two conditions still hold. First of all, I want to check that AI prime still divides AI plus 1 and AI minus 1 still divides AI prime. How to prove these two things? This AI prime is equal to bi. And this AI plus 1 is equal to bi plus 1. And as I said, we look at the place where bi divides bi plus 1. So this is simply true because we found such a place where this segment ends, but still bi divides bi plus 1. So in this place, this holds, and that's why it's fine. Okay, now what about this one? As for this one, AI prime is equal to it is equal actually to bi, which is equal to aiy. And you know that ai minus 1 divides ai. It of course means that ai minus 1 divides ai prime because ai prime is a multiple of aiy. So it's bigger, it's a multiple of AI, so it is also true. Okay, so in the smallest possible set S, there are no such places where a segment ends, but bi divides bi plus 1. Okay, but then I claim that you can just take this y. Why you can take this y? Because there are 4 cases. The first case is 2 numbers from the same segment. I claim that if you divide both of them by x, then they divide one each other. This is because when you take y and divide both by y, they divide each other. That means that simply bi divides bi plus 1 there. But if I divide them by x, they also divide each other. The same thing holds here. Third case is this place, so bi and bi plus 1. But then it is true because x divides this strange fraction. And if x divides this strange fraction, no, yeah, x is divisible by this strange fraction because x is divisible by all such strange fractions. Therefore, it has to happen that here bi plus 1 divides... I mean, it has to happen that ai over... Sorry that it is not very clear, but it's actually very easy. So again, we have some segment which ends here. I have bi and bi plus 1. And I say that ai should be bi over x and ai plus 1 should be bi plus 1. So I claim that ai, of course, divides ai plus 1. This is because ai equals bi over x. It should divide bi plus 1. And x, so it should happen that bi divides x bi plus 1. And I actually chose such an x that it is divisible by all such fractions. So in particular, x is divisible by bi plus bi over GCD bi and bi plus 1. Good, and basically it's true. It is basically true because bi plus 1 is divisible by this thing and bi is divisible by bi. Okay. Last place is this one. But it's kind of obvious that since y is good as well, it has to be true that y divides x. Actually, when I say that x is an LCM of such fractions, actually, this is just the minimum possible x that is good for this problem. If you take any x which is not divisible by at least one of such fractions, then there will be a problem at the corresponding place. Therefore, y is divisible by x, and if in this place you divide by y and still bi plus 1 is divisible by bi, then if you divide by an x which is a divisor of y, you still get that bi plus 1 is divisible by bi. Let's write that formally. We know that bi divides bi plus 1 over y. I want to prove that bi divides bi plus 1 over x. This is equivalent to y bi be divisible by bi plus 1. This is equivalent to x bi be divisible dividing bi plus 1. And since y is a multiple of x, then if this divisibility happens, then this divisibility happens. The last thing that actually we skipped is that all numbers should be integers. All numbers should be integers. I claim that if with this y all numbers are integers, then with x all numbers are also the integers. It's also true. So the fact that bi over x is integer follows from the fact that bi over y is an integer. Why? Because bi over x is equal to bi over y times y over x. And y over x is an integer. And bi over y is also an integer. Then bi over x is also an integer. Great. Problem D. Make a palindrome. It's an interesting problem. So what is the problem? You have an array and you have chosen some number k. You do this following operation several times. You take any segment, you take any number which is exactly a kth order statistic in this array, and if there are several kth order statistics, you take any of them, and you remove that from the array. The question is, can you get a palindrome after all such operations? Okay, for example, if I have I1, 2, 3, 3, 3, and k equals 3, then each operation will eliminate one of the threes. So I cannot ever remove this 2. And since I can't, at some moment, at any moment, there will be exactly 1, 1 and exactly 1, 2. And you cannot have a palindrome where there are exactly 1, 1 and exactly 1, 2. Because each digit or character except 1 should be even number of times. Okay, how to solve this? Actually, I claim that let's look at all numbers in this array. And let's sort them. A1, A2, A3, etc. AN. Okay, this is our array. Let's look at a kth. Okay. I claim, first of all, I claim that all numbers less than ak have to stay in the array. Why is that? Because you cannot do anything so that any of these smaller numbers, strictly smaller numbers, is a kth order statistic in some subsegment. In order for an element to be a kth order statistic, you need at least k-1 elements that are less or equal than your number x. But for any number strictly to the left of ak, which is less than ak, there are at most k-1 elements, which are at most x, but if we don't count x, then there are at most k-2 elements. That's too few. So all elements less than a kth will stay where they are. They will not be erased from the array. Conversely, any element which is greater than ak, you can remove. Why is that? Assume that you have gotten some palindrome. You have got some palindrome. Then you can remove all elements which are greater than ak, and this is still a palindrome. Moreover, you can but do we want actually? Do we actually want to remove all elements which are greater than yeah, I think I guess we okay, I will prove. I can actually prove now. I can prove to you that at any moment you can remove any element which is greater than AK. So that we can remove all of them and we still have a palindrome. Okay, let's understand that. So let's take our array. I claim that if there is still an element which is greater than AK, then we can remove it. For that, I will prove to you that there are, let me write you a statement. There are always at least k elements which are at least AK. No matter what you do, you will always have at least k minus 1 elements which are at least AK. Which are at most AK, sorry. There are always at least k minus 1 elements which are at most AK. How to prove that? Assume this is true before some operation. Then we do some operation. In this operation, there was a segment. In this segment, there were at least k elements. Right? There were at least k elements. So let's consider two cases. First case is that all these elements, there are k minus 1 minimum elements, and they are all at most AK. Then after the operation, there are still these k minus 1 elements, and they are still at most AK. So first case is that in the segment, minimum k minus 1 elements are at most AK. Then this is easy. The second case is that among minimum k minus 1 elements, there is at least one which is greater than AK. But that means that the kth order statistic is also greater than AK. And if it is greater than AK and we remove it, then we did not remove any such elements which are at most AK. So the fact is true. So at any moment, there are at least k minus 1 elements which are at most AK. This is a fact. Okay, what to do with it? Now let's look at any element. Now I want to prove that there is a segment. There is a segment. Let me write the full statement. So if there is element x in A such that x is greater than ak, then, and only then actually, there exists a segment in A such that kth order statistic in this segment is greater than ak. This is what I claim. Okay, let's prove that. Let's prove that. Actually, I even may not need this fact, but okay. Assume that the upper thing is true. Here is our segment. Let's find there this element x. Okay. I know where I will use that. So this x is greater than ak. This is one element which is greater than ak. But also there are at least k minus 1 elements which are at most ak. They are not equal to x. So there are at least k elements in this segment, just because there is a big element and k minus 1 small elements. So if this segment is of length at least k, then let's take any segment of exactly k elements which contains x. Its kth order statistic is at least x because it is just the maximum of this segment, and maximum is at least any number in this segment. So there is kth order statistic which is at least x, so it is greater than ak. So we will remove it, or any equal to it number. So we will remove something that is greater than ak. So that's the end of it. And so we can remove always, so if there is at least one element which is greater than ak, then we can remove it. And we will remove it until there are no such elements. Now the question is, so let me write it. There exists answer if and only if there exists answer where all elements less than ak stay, all elements is greater than ak gone. What about elements which are exactly ak? Some of them will vanish, some of them will not. How many of them will stay? Actually, we want that the final length of the array is at least k minus 1, simply because there is a statement upper. The length of the array in the end will be at least k minus 1. Therefore, we want at least k minus 1 minus number of elements such that they are less than ak. This is how many ak's exactly we want. So the solution looks like this. First of all, find ak. For example, you can take b equals a, then sort b, then take simply b k minus 1. This is in 0 indexation, and this k was in 1 indexation, that's why I say it. So we know ak. ak with parentheses means kth order statistic of a. The second operation is just remove all elements greater than ak. We don't need them. Anyway, we can remove them in the end. Then why not remove them in the beginning? The third thing to do is let's take all elements which are less than AK, and they should be a palindrome. If they're not a palindrome, then the answer is false, because they still are they should be in the array in the end, but they are not a palindrome. Then that's bad. It's not symmetric anyway. For example, if we have AK equals like 3, and I have 1, 2, 1, 2, and for example 3, 3, 3, 3, 3, something like this, and here 5, 6. You can remove 5, 6, but you cannot remove this 2. And if you only take elements which are less than 3, you have 1, 2, 1, 2. This is not a palindrome, so the answer will always be no. Okay, now let's assume that the green elements are palindrome. Then all you need is symmetric number of 3s. So for example, here there is 1, 3, so here it always also should be 1, 3. Here there is 1, 3, but here we have 2 3s, so we will have to remove one of them. Formally, let's assume that, let's denote by T the number of such elements. So there are T elements which are less than AK. Let's call them now C1, C2, etc. CT. Then there are T plus 1 places, and in each of them there can be several AKs. Several AKs here, several AKs here, several AKs here, etc. Let's call the numbers of such elements n0, n1, etc. nt. In the end, it will become m0, m1, mt. But in the end, these numbers m's should be a palindrome, because if you want this array to be symmetric, you want m0 equal mt, m1 equal mt minus 1, and so on. So you are given a vector of integers, and you need to find the maximum array, which is at most this array, but is a palindromic array. And for that, you replace each number with minimum of this number and the symmetric one. In the end, you add up all numbers which are less than AK and the sum of this symmetric array, and you get the answer. Okay, we now have E and F. Okay, problem E. We do several operations of the following form. We take an array B, which is at most A, and B should be divisible into two parts in which left half is same as right half. Okay. We want to make the minimum number of operations. Actually, there are always at most 2 operations or impossible. You can read the proof in the editorial, but I will just explain to you. So first of all, let's find sum of this array. So if S is odd number, then it is impossible. Why is that? Because each time you do an operation, in this operation the left sum and the right sum is the same. So the sum of array B is even. And actually AI can be decomposed into sum of such BIs. If in the end you have zeros, then A is just the sum of several B's. And since in each B the sum is even, then in A the sum is also even. That's why I say that it is impossible. Second thing, if there is a too big element, then it is also impossible. So if there is an element which is greater than S over 2, then impossible. Let me call it exists AI. which is greater than s over 2. Why is that? I claim that after any operation, it still holds that AI is greater than a sum of all other elements. We can rewrite it as AI is greater than S minus AI. It is equivalent. So I claim that you cannot have any element which is greater than sum of everything else. Why? Because let's look at one operation. In one operation, we take some array B, and in which in this half and in this half has the same sum, and subtract. So we have some element AI here. This is the biggest element. We subtract something from it. We subtract y, for example. But we subtract at least the same amount from the right side. That being said, you subtracted y from AI, but you subtracted y from this AI, but you subtracted at least twice y from S. You subtracted y from S by subtracting this y, subtracting with this y, and also you subtract some other numbers probably. So this inequality still holds. So this is a red flag. We will not get an answer if this or this holds. So there is only one case left. Oh, actually, there are several cases, but in this case, the answer is true. And there will be either one or two operations. So let's say that we have m equals s over 2. And let's say that there exists a prefix such that sum of this prefix equals m. So there is a big array, and there is such a prefix in which this sum is m. This automatically means that in this suffix, the sum is also m. This is actually equivalent, that you have a prefix with some m and that you have a suffix with some m. These two are equivalent. In this case, you can vanish it in one operation. You can in one operation make it 0. And the last case is that you have no such prefix. Let's take the longest prefix, which is at most m. By what we have done before, this longest prefix is strictly less than m in sum. Otherwise, that would be the third case. And let's take the longest suffix, which is at most m. I claim that there is exactly one number here. There is exactly one number because if there were two numbers, you could either add this here or add this here. And if you cannot do both, then this sum is greater than m, and this sum is greater than m. But then their total sum is greater than 2m, which is s. And you cannot have sum of such some elements greater than s. Okay, what to do then? So you have some array, then you have some number, and you have some array again. This is at most m, this is at most m. That's it. I claim that this sum is greater than m, because actually this is smaller than m, and this is smaller than m. But since the total sum is 2m, then this thing is greater than m. Then let's say, let me draw it somehow else. What do I want to say? I want to say that this sum is less than m, then it is m minus a, for example. And this right sum is m minus b. Then this thing is a plus b. I actually want to subtract a from this number and from this number. This is what I want. So first operation is divide like this, subtract a here and subtract a here. Why we can do it? Simply because this is at least a and this is at least a. This is at least a because m minus a minus b is at least 0 because m is at least a plus b, because m is at least this element, because any element is at most half of the array. And we proved that in the point 2, in the item 2. So therefore, this number a is at most m minus b, and this means that we can choose some smaller array with sum exactly a and subtract it. After we do that, this is m minus a in sum, this is exactly b, and this is exactly m minus a minus b. And after that, you can just divide like this and finish the proof. So we can do it in 2 operations. Why couldn't we do it in 1 operation? Because if we can do it in 1 operation, then simply b equals a, and that means that a can be divided into 2 parts with equal sum. But this is exactly case 3, which we have already considered. Okay, finally problem F. Problem F1 was solved by me, problem F2 is not solved by me. I don't know what to do there, but it is simply a dynamic programming. It is 2-dimensional. Let's say that dp n is how many ways to make a good array of length n with all restrictions I. dpi is the number of good arrays on indices from 1 to I. And any element which is any element outside of this part, these restrictions are ignored. Only restrictions inside of this segment. We look at them. Why did everything... Where is everything? Ah, okay. From everything from 1 to I, all these restrictions hold. Then what I want to say? I want to say that assume that I know dpi. Let's try to add one more segment. So I have some array from 1 to I, and I add one more segment of length j. So let's iterate over I and over j. Then there are j ways to do it. However, there are j cyclic shifts. So you actually will multiply your answer by j. You could do that, but you have also restrictions. Each restriction, there are actually 2 types of restrictions. First restriction is such number, so it is not equal to q, for example, and on the position r. What does it say? So this element cannot be q. This element cannot be q minus 1. This element cannot be q minus 2. Let's go until we hit 0. We can hit 0 2 ways. We can hit 0 still being here, or we can reach the left end, teleport to the right, continue there, and get 0 somewhere here. It actually only depends on whether r minus y and q compare somehow. For example, I guess, okay, if we are in 1 indexation, then I want to find out when we reach 1, not 0. There are 2 cases. Case 1 is that r minus I is greater or equal than q, that means that we will reach 1 before teleporting to the right part. Or r minus y is less than q. Let's store all such restrictions in one Boolean array. So each time we hit a restriction, we make some Boolean false. Which Boolean is false? Let's say that we keep track on where a 1 can be. So if there is such a restriction, then 1 cannot be in the position I minus in the position r minus q plus 1. So it cannot be here. So if I see this restriction, I say that b r minus q plus 1 is false. Otherwise, this number is negative. If you know Python, you know that in this case, you go the other way. So this means that r minus q plus 1 plus j element cannot be 1. And this changes with your j, but number j minus... Yeah, this changes with your j. But this number is constant. And you can actually store it in another Boolean array C. So like q minus r minus 1 is false. So B keeps track of restrictions that are attached to the left edge of your array. They do not change when j grow. And there are some restrictions which are attached to the right part, right edge of the array. So they move when j grow, but they move the same speed as j. So if you move j 5 positions to the right, then the restriction also moves 5 positions to the right. And we can keep track of that by fixing this number. Okay, so now we know all the restrictions. And we simply calculate the answer. So we find the number of positions where 1 still can be, according to all these restrictions. And we find that there are p ways of doing it. And you add p times ans I to the answer. However, if you do that, you will calculate the same array several times. For example, 1 to 1, it can be achieved like this and like this. The most beautiful way to eliminate this problem is to say that your arrays are greedy. So each time you start an array, you take the longest possible array. So this is impossible because this is not greedy. If you started with 1, you can go on and take 2, etc. So 1, 2, 1. It can be proved that you can take segments greedy. You can read that in the editorial, or like move hour and a half in the past, and I proved that during the contest. Okay, what then? We do it greedily. Then the only thing that should be restricted is to take some segment which starts in 1, ends in k, and then you cannot have the next segment starting with k plus 1, because it is not a greedy behavior. Instead of that, you could go on, take this k plus 1, etc., take s, then there will be 1, 2, and some number k, and you could stop here. This would be the greedy partition. So you never have a segment 1, etc., k, and then the next segment starting with k plus 1. So let's make our DP two-dimensional. our DP should be two-dimensional. So now we have ans ij, which says the following. Ans I0 is just all answers, and ans ij is the number of answers that end with a segment 1 to j. Okay, how to calculate this new thing? So first of all, you can calculate ans ij just here. 1, 2, etc. j is exactly the segment where 1 is here. So you check if the restriction allows 1 being here, and if it allows it, you just add the corresponding partition not only to the answer I0, but also to the answer I and this left element. Now the problem, how to forbid this situation. You just say that answer I, j, answer I0, I plus j0, you should subtract ans ik if it is allowed to start here with k plus 1. So if this starts in position k plus 1, then where is this 1? You can find this out. So you know that if you have a segment of length j and it starts in k plus 1, then there is 1 somewhere. Then find out what restrictions allows or disallows it. You find this restriction and you subtract, and if this restriction allows 1 being here, then you need to subtract this from this. And you do that for each k. This solution works in O of n cubed. So this is fine for f1, but not for f2. Okay, I think that's it. Thank you for watching.